Students, last video we learn how to write the different formulas of glucose in Fisher projection formulae and perspective formulas. Now in this video we will learn the formation of hemiacetal from D-glucose, formation of hemiacetal form from D-glucose or from glucose, that is from open chain or from Fisher projection of glucose get converted to cyclization or the ring formation, and that structure or that projection formula are known as Howard projection formula. So in this open chain structure of glucose converted to cyclic structure by a hemiacetal formation. So what is hemiacetal formation? This is a characteristic reaction between the aldehyde group present in glucose molecule and alcohol. So in glucose reaction, this hemiacetal formation reaction is a free aldehyde group present at C1 and C5OH group. It is combined to form a 6-membered pyranose ring. Why it is pyranose ring? Because this is a derivative of pyrene. So all of you know this glucose structure. 1, 2, 3, 4, 5 and 6 carbon. So first carbon is CHO, last carbon CH2OH, and in glucose third carbon OH on left hand side, and as this is the D-glucose, fifth carbon is on right hand side. So the reaction of carbonyl carbon and fifth carbon OH. So suppose we can draw the coil structure. This is what C5OH, this is C4, C3, C2 and C1 carbonyl carbon. So interaction takes place in between the C5OH and C double bond O. You will get this pyrene ring. So this is C1, C2, C3, C4. This is what your pyrene ring. So here in a pyrene ring there is no free aldehyde group, as it forms the oxide ring. Now this oxide ring is not stable, it is a weak. It opens with the strong reagent like SCN or oxime H2S, SCN, NH2OH or phenylhydrazine PHNH, NH2. So with this reagent, this ring will be open and form the corresponding derivatives. But with the weak reagent, for example NH3, then bisulfide, these reagents are unable to open this ring. So it cannot react with this, these reagents cannot react with this glucose. Now, when the interaction takes place, or this open chain or the ordinary glucose dissolve in water, and then it was observed that this is the ordinary or the natural glucose. When dissolved in water and when it crystallize at room temperature, then the crystals will get the pure crystals which shows melting point 146 degree. So, this crystals melts at 146 degree, and if this crystallize above 98 degrees Celsius and rapidly cool down, so whatever the crystals are formed, pure crystals are formed, it shows melting point 150 degree. So, these two are the different isomeric form of a glucose. So, this can be explained on the formation of hemiacetal formation with these two different form. So, we see how these two different form will get from open chain. So, suppose we can explain this C double bond O, OH, OH, and this is your C5OH, CH2OH. So, you just write this on horizontal form. So, here this C1 carbon atom this is C2 OH, this is C3 OH on above the plane, then C4 OH below, then C5 OH below, and here is the CH2 OH. Now, if you can write down the coil structure, just C double bond OH, so this is carbon number 1, 2, 3, 4 and 5. So, whatever you OH are below the plane, you can write down it below the plane. So, C2OH below the plane, C3OH above the plane, C4OH below plane, and the C5OH. Now, if you can rotate this C5OH, this will be above the plane CH2OH, and interaction takes place here. So, this will give you two isomeric form of so here once the ring is formed, you will get this carbon is a asymmetric carbon. So, if you can rotate this carbon, then you will get the another stereoisomer. So, what is the difference between these two isomer? The difference is at C1 position. So only the orientation of OH at only at C1 position, therefore these two are apimer. And these two are diastereomer, because they are two different isomers. These rings are very weak, so if you can hydrolyze, it will be open. Now this form are known as alpha isomer. Why it is alpha? Because orientation of this OH are opposite to the orientation of C6OH. So these two are opposite in direction, therefore alpha. So this is called as the alpha form, and this pyranose, you can write down this alpha glucopyranose. This OH and this OH, they are on the same position, and therefore they are beta. So therefore it is beta glucopyranose. As this is D, therefore we can write down D glucopyranose, D alpha glucopyranose and D beta glucopyranose. These two are called as an anomer, and this C1 carbon are the anomeric carbon. So in glucose, in the ring structure of the glucose, if this carbon atom which is hang between these two oxygen atom, this carbon atom, here is oxygen atom and here is oxygen, this is the middle carbon. So this carbon atom is called as anomeric carbon. Now this pure form, when in 1846 the scientist he discovered that when this glucose dissolved in water and he took the optical activity of a solution. So what he observed? He observed that the optical activity get gradually changes from initial. So he observed that this alpha form, it shows optical activity plus 12 degree, and with time it gradually decreases and it remains constant at plus 52.7 degree. And when he noted the optical activity of beta form, so it initially it shows plus 19 and gradually it increases to plus 52.7. So this change in optical activity with time is termed as mutarotation. So what is meant by the mutarotation? It is the spontaneous change in specific rotation. Mutarotation is the spontaneous changes in specific rotation of optically active solution without any changes in other properties. Other properties is known as mutarotation. So, this mutarotation is a characteristic property of this glucose exhibited by the hemiacetal formation that are free form of a open sugar. So, because of this hemiacetal formation, this C1 becomes new asymmetric carbon atom, and therefore, the two stereoisomers are possible. These are the alpha form and beta form, and they are known as epimers or anomers because they differ only at one configuration, only at C1 position. In a cyclic form of a glucose, they have total 5 asymmetric carbon atom at C1, C2, C3, C4 and C5. So, total 5 asymmetric carbons are 5, and the cyclic form shows total 32 optical isomers. How it is? By Ventov formula, if you can put 5, so 2 raised to the 5 you will get 32 optical isomers. How many optical isomers in open shell formula? Because it is 4 asymmetric carbons atom. So, 2 raised to power 4, 16, but in cyclic form it shows 32 optical isomers. Now, we can write down this both form or both cyclic Hobart projection into a chair conformation. So, how we can write down in chair conformation? So, this oxygen, so this is C1 carbon, C2, C3, C4, C5. So, this is alpha. In alpha you can show at axial OH, here is the equatorial OH. This is down, that means at equatorial OH. This is again up, equatorial OH. Here is C5 again up, that means it is C4, it is equatorial OH, and C5 again it is equatorial. So, what you observed in alpha, C2, C3, C4, C5 all are equatorial OH, alpha form. Now, beta form, here this OH at axial equatorial position, and H is OH, OH, OH and equatorial. So, in beta form all OH are equatorial position. So, in equilibrium concentration, this alpha form are 33%, this alpha are 38%, and this beta form are 62% in equilibrium formation. These open chain are negligible or it is less than 0.5%. So, what we learned today? How the hemiacetal formation, then because of this hemiacetal formation there are two possibilities to form the stereoisomers. One is the alpha form and another one is the beta form. So, when we took the rotation, what happened? From initial stage to the particular stage, it shows gradual changes, and that changes of optical rotation is nothing but the mutarotation. So, what is mutarotation? Mutarotation is the spontaneous changes in specific rotation of optical activity of optical active solution without any changes in other properties. They are known as a mutarotation. Thank you.